Welcome to the 11th lecture for the NPTEL course on computer system optimization for machine learning. Today I will give you a brief recap on whatever we discussed in the last lecture, and then we will discuss about the data flow for DNN execution. Okay. Now, in the last lecture we discussed the different or we summarized many popular DNNs, and we saw that the number of weights and the number of multiply and accumulate operation for different DNNs actually vary, and then the recent DNNs has lot of weights and the multiply accumulate operation. For an example, if you see ResNet 50 has like 25.5 million multiplied and 25.5 million weights and then 3.9 billions of multiply and accumulate operation, right. Not only that, VGG 16 has like 15.5 billion multiply and accumulate operation, which is like extremely high, correct. So, since we have this high number of multiply and accumulate operation as well as the number of weights, we need to do something, we need to do some trick, we need to have some new technique to computation, so that the execution time is less. And for that we discussed something called depthwise separable convolution. There are two steps in depthwise separable convolution. One is depthwise convolution and another step is pointwise convolution. In depthwise convolution, let me go to the previous slide. In depthwise convolution, we have this 12 by 12 by 3 image, which is getting convolved with 5 by 5 by 3 kernel. But then in regular convolution, if you remember, once we convolve with the kernel, then we accumulate across the channels, right. But in depthwise convolution step, we do not accumulate across the channels. So, the output is 8 by 8 by 3 image. Now, in the next step, that 8 by 8 by 3 image actually gets convolved with, as this is called pointwise convolution, and then this 8 by 8 by 3 image gets convolved with this 1 by 1 by 3 kernel to get 8 by 8 by 1 image, and then we have 256 of all the of that 1 by 1 kernel to get 8 by 8 by 256 image. Now, of course, these numbers are imaginary. We might not always have like 8 by 8 256 and all those things, but the thing which is constant of about depthwise separable convolution is there are two steps. One is depthwise convolution, another is pointwise convolution, right. And then we also saw that the number of multiply and accumulate or the number of multiplication is reduced drastically in case of depthwise separable convolution. Now, today we will talk about the data flow for DNN execution, right. Now, before we like go deep dive into the different data flow of DNN execution, let us first see what is the memory access bottleneck of DNNs. Now, in the worst case, so remember in DNN we have lots of weights and then they are producing lots of activations, and there are lots of things happening. So, whenever we are producing activations, so remember the activations which are produced by layer I has to be used by layer I plus 1. Right. That means those activations are stored in the memory, and then layer I plus 1 fetches from the memory and all those things happen, right. So, in the worst case, all the memory read writes can be occurring from DRAM accesses. It might be the case that none of the L1, L2, L3 caches are being used, everything are getting accessed from DRAM, right. That is the worst case. Of course, in the usual case there is some cache access also. Now, in AlexNet there are 724 million max multiply and accumulate operation, right. And then if you actually do the calculation, you will see that for each MAC we need one read, one write, and then you have to you need two read and two write, because you need to read the weight, you need to read the activation, and then again you will write back the weight and then you will write back the activation, right. So, there are 4 read write access for each of the multiply and accumulate operation. That means we will have total 2896 millions of DRAM accesses, like that is like almost 3 billions of DRAM accesses, which is huge, right. So, that is why we need to perform data reuse. When we say data reuse, that means we will put some of the activations or some data in the cache, so that those data can be reused for further computation, right. Now, let us see what are the different data reuse or different types of data reuse in DNN. there are like broadly 3 types of data reuse in DNN. One is convolutional reuse, another is feature map reuse, and then filter reuse. In convolutional reuse, we tend to reuse the convolutional layer only, the sliding windows only. So, you can see this filter is getting convolved with this input feature map, right. Now, when we perform this convolutional operation, then we most likely fetch this filter weights from the DRAM, and then we fetch the corresponding patches of input feature map from the DRAM, and so on and so forth, right. Now, whenever the convolution is done, then we probably put the patch, or we probably forget that patch and then do the next convolution, and so on and so forth. But then see, there is some overlap, or the same patch of the input image can be used again and again, can be used for another convolution. So, rather than forgetting the entire patch, which was entire patch of input feature map, which was just got convolved, we can reuse some of the pixels in the patch, so that we don't need to read all those pixels of the input feature map all the time. So, that is the convolutional reuse, and that occurs in convolutional layers only, right. Then there is something called feature map reuse. So, remember, we have these filters and there are multiple of these filters. So, all those filters will get convolved with the same patch of the input feature map. So, if we see one particular channel, let us say the first channel, this first channel will always get convolved with this particular patch in the first channel, right. So, that means what we can do, we can store this particular patch of all the channels of the input feature map in the cache, and then we can reuse it again and again for different filters, right. We can probably fetch different filters from the main memory and then convolve with the same patch, or yes, convolve the same patch which is stored in the cache. So, that is the feature map reuse, and it can be applicable to convolution as well as fully connected layers. And then finally, there is something called filter reuse. As the name suggests, you can think that we have one filter and then there are multiple input feature maps, right. As I was saying again and again in probably last lecture, that there is no I mean, usually we do not perform one inference, but rather we perform multiple inferences in a batch, right. Now, if we have a batch of n inference, then we can pick a filter, put it in the cache, and then we can perform the convolution operation with the filter for all the input images, right. So, that is called filter reuse, and it can happen for convolution as well as fully connected layers, right. Now, if all type of data reuse is utilized, of course, it is hypothetical, we might not be able to reuse, or we might not able to launch all types of data reuse, then, but if hypothetically if we can utilize all the type of data, then the DRAM access in AlexNet can be reduced from 2896 million to 61 million, which is of course a best and hypothetical case, but you can see the power of reuse, right. From 289, if we do the reuse, it will, the number of DRAM accesses will be reduced from 2896 to 61 million, right. It is like 40 times or maybe close to 50 times reduction, which is great, correct. Now, in that context, let us first discuss about systolic data flow, and then we will introduce different data flows of DNN computation. Now, again, whenever we talk about DNN or any large machine learning algorithm, the most time consuming or the most resource consuming part is matrix multiplication, right. So, let us see how to perform the matrix multiplication in an efficient way. Let us say we have two 4 by 4 matrices, we have this A which of size 4 by 4, B of size 4 by 4, they are getting multiplied to obtain another 4 by 4 matrix of size, another 4 by 4 matrix C of size 4, another matrix C of size 4 by 4, right. So, we have like A11 to A44, B11 to B44, C11 to C44, and then I mean, you know, typical matrix multiplication, C11 will be A11 multiplied by B11, A12 multiplied by B21, A13 multiplied by B31 plus A14 multiplied by B41, right. That is how the matrix multiplication happens, correct. Now, let us see how to optimize this matrix multiplication, right. So, let us say we have P's. So, P is nothing but processing element. So, one processing element can do multiply and accumulate. So, P is nothing but processing element, and this processing element can do multiply and accumulate. It can multiply two numbers, and then it will add with the previously saved number. Okay. So, let us see with this P structure or with this P, how can we perform this matrix multiplication. So, let us say we have 16 P's, P11 to P44, and then the data is flown like this, right. So, A11 to A14 is here, B11 to B41 is here, right. Now, we will see how why these zeros and all are there, we will soon see. Now, so remember, everything in the hardware happens in clock cycle. So, you can think that in your clock there is a second hand, right, which counts every second. I do not know how many of you use analog clock, everybody now use Fitbit or the Apple Watch, but if you use analog clock with like 3 hands, then you will see that there is one hand of second which ticks every second, right. So, you can think that at each tick something happens in the hardware, some processing happens in the hardware. Now, here in the name of processing, let us say we are performing multiplication and addition. Okay. Now, in the first clock cycle, P11 will get B41 and A14. So, this B11, so A14 and B41 will get added, right, and let us also assume that all these P's are initialized with 0, right. Now, in the second clock cycle, so this data is flowing, all these B values are flowing vertically and these A values are flowing horizontally. Okay. So, these values are flowing. Okay. Now, that means in the second clock cycle this B41 will reach here, and then A24 will reach here. So, remember, in the first clock cycle 0 was there and nothing was there. So, 0 multiplied by 0 plus previously saved value is 0. So, there was only 0 in the first clock cycle. Now, in the second clock cycle P11 will get B31 and A13. So, B31 will get multiplied with A13, and then the result will get added with the previously saved value. The previously saved value was nothing but the product of B14 and A14, right. Now, similarly, in the next clock cycle this B21 will get multiplied by A21 and get added, B11 will get multiplied by A11 and then get added. Now, if you see, what we actually did is we actually first did A14 plus B41, A13 plus A14 multiplied by B41 plus A13 multiplied by B31 plus A12 multiplied by B21 and then A11 multiplied by B11, right. So, that means from P11 after the 4 clock cycle we will actually get the value of C11, right. Now, that is how all these P's are actually calculating different elements of the outputs. Okay. Now, how this let us see how this P44 will get calculated, or C44 will be getting calculated at P44. See, at first clock cycle this will get 0. So, at first clock cycle this will get 0, P44 will get 0, in second clock cycle also it will get 0, third clock cycle also it will get 0, fourth clock cycle also it will get 0. So, it will get this value B44 at 7th clock cycle, right, because remember at first 3 clock cycle anyway nothing is coming. So, it will get 0 0 0 and then 3 zeros are flown, and then B44 will be propagating here at 7th clock cycle, right, and then at the same time A44 will also come, right. Then that means we will multiply this B44 and A44, and then in the subsequent clock cycle this A43 will get multiplied with B34, A42 will get multiplied by B24 and A41 will get multiplied by B14 to get this C44, right. So, that means at 7th clock cycle it is getting the first output, and then 8th, 9th, 10th, after 10th clock cycle all the outputs will be computed, and that is this is the last output of the matrix of the output matrix which will get computed, right. Now, this particular data flow is known as systolic data flow, and here the biggest advantage is we can do seamless pipelining. So, let us say after this C is equal to A plus B, C is equal to A multiplied B, we want to do another multiplication D equals to E multiplied by F. Then that elements of E and F can be started flowing here as well as here, right. As soon as this A11 is done, we can have some controller saying that after 4 multiplications are done, that after that we are starting a new multiplication, right. So, we can start flowing this E11, E14, E13 etc. in these places, so that we can have a seamless pipelining between two input in this systolic data flow. Remember, this systolic data flow for matrix multiplication is extremely important, and in many of the accelerator, talk about any of the recent NPUs from AMD or Qualcomm or Intel, they use this systolic data flow in some sense or other. Okay. Maybe not exactly like this, but the base is systolic data flow. Now let us talk about different types of data flow which is prevalent in the DNN computation. There are 3 unique type of data flow for DNN computation: output stationary, wait stationary and input stationary. Okay. So, most likely we will not talk about all these 3 data flow in this lecture, but eventually probably in the next lecture we will talk about all these 3 data flow. So, let us start the discussion with output stationary. Okay. Now, the goal of this output stationary data flow is to use the goal of this output stationary data flow is to minimize the partial sum read write energy consumption and maximize the local accumulation, right. Now, whenever we talk about these different data flow, we will talk about P. I think in systolic data flow only we have briefly talked about P, but let us see how exactly the P looks like. So, this is the structure of one P where we have these multiply and accumulate operations. So, let us see there are 3 input, one is from wait buffer, one is from input activation, another is output buffer. So, this matrix, this multiply and accumulate unit takes one input from wait buffer, one input from input activation buffer, it multiplies, it computes the product and then adds with the value from output activation buffer or the previously saved value. Okay. And then it either reads to the output reads from the output activation buffer, that is why there are double headed arrow, or it writes to the output activation buffer. Okay. So, basically this multiply and accumulate operation, what it does is, let us say there is wait 1 or wait t multiplied by activation t, and then it adds with the activation which was produced at the timestamp t minus 1. So, something like that. Okay. That is what is one P. So, remember in one P we can have one buffer with just one slot where we can put one wait, one input activation and one output, right. Now, let us discuss this output stationary data flow in terms of 1D convolution. So, 1D convolution is nothing but it is a simpler case of 2D convolution. So, let us say we have this wait and then we have this input. So, we can just convolve this weight over the input, I mean we can slide this weight on the input to get the output, right. If the length of weight is r, if the length of input is h, then the output length will be h minus r plus 1, assuming that the stride length is just 1, stride length is 1. Okay. Now, we can easily write a C program for this convolution. We can just say that for e equals to 0, e less than e plus plus, for r equals to 0, r less than r plus plus, output of e equals to I multiplied by e plus r, that is the sliding window thing. Okay. by the way, I, W and O are nothing but the input activation, filter weights and the output activation. So, I E plus R multiplied by W R. Now, one important thing is there is no constraint on loop permutation. We can exchange the loops, still we will get the same result. Okay. But in this particular case, what we can see is the outer loop is the E equals to 0, right, or outer loop is iterating over the outputs, right. Now, that means here whenever we are actually computing the output, every time for different input the output index is same. So, let us say E is 0 and then we started R equals to 0, R less than R, then output of 0 will be first computed, right. Output of 0 equals to I 0 plus I 0 multiplied by W W 0, then I 1 multiplied by W 1 and so on and so forth, right. So, here the E is constant when R is varying, since we have written this iteration over the output in the outer loop, correct. So, this is, that means the output, like we will get one output or we will compute all the partial sums for one particular output at once, correct. So, that is the philosophy behind this output stationary data flow, right. Now, I think we have discussed this thing, that for the above loop we essentially duplicate the weights on all the P's. So, what we can actually do, I already showed you the P structure. So, we can have multiple P's for multiple outputs, right, and for each of the P we can duplicate the weights. So, remember, to get the output we need to use same weights again and again, right. Now, the input activation in one window will go over all the P's and then the execution moves to the next window and so on and so forth. When all the windows are completed, each P gets the outputs locally. So, that is the output stationary data flow. Now, let us see the reference pattern. Okay. So, the same code, we have the same code for E is equal to 0, E less E, E plus plus, and for R equals to 0, R less R, R plus plus, or output of E equals to plus equals to I input of E plus R multiplied by W. That is the convolution operation, right. Now, let us have this parameter layer shape of different layer shape, H equals to 12, R equals to 4 and E equals to 9. Again, H is nothing but the input size, R is nothing but the output size, R is nothing but the filter size and E is nothing but the output size. Okay, I will just write H is input, R is weight and E is output. So, if we closely look at the reference pattern, like which indices are being referred, we will see a different, like we will see a like very unique pattern. So, this particular pattern is for output. You can see that at first cycle E is equal to 0 is fixed, right. First cycle E will be 0, R will be 0. So, that is why we have E as 0 and then R as 0. Then we are also accessing the weights of 0, right, the 0th index of the weight. In the second cycle again E is still 0, we have changed the R as 1 and weight is also changed, right, and then in the third cycle still output is 0. So, output index will not be changed until and unless the same output is completely computed, right, and to compute the output we need all the 4 weights, we need all these input indices, right. So, again for the next 4 cycle, again you can see that for the next 4 cycle the index output index will be fixed at 1, but then now we have this sliding window of weights or sliding window on the input. So, initially in the first 4 cycle we access 0, 1, 2, 3, now we will access 1, 2, 3, 4 indices of the weights, and then the same indices of the weights will have to be used again and again, like 0, 1, 2, 3, 0, 1, 2, 3 and so on and so forth, right. So, that is the reference pattern during output stationary data flow, right. Now, again I mean these observations probably I already covered. So, single output is reused many times, like specifically R number of time they are getting used, and then all weights are used repeatedly. So, you can see that the same weights are getting used repeatedly, right, 0, 1, 2, 3, 0, 1, 2, 3, they are repeatedly getting used. And finally, if we see the input, we have a sliding window of input of size R. So, you can see this this is the pattern of the input access, where one sliding window is helping to access the input, right. So, these are the output stationary reference pattern of output stationary data flow. Now, let us talk about the buffer data access for output stationary data flow. So, the number of multiply and accumulate operation is, I mean, you can see it is E multiplied by R. We cannot do this any convolution without this number of multiplication. E multiplied by R is the number of multiply and accumulate operation. Number of weight read is also E multiplied by R, because we are not reusing the weight. At each cycle we are using different weights. So, in the first 4 cycle we will use 0, 1, 2, 3, and then again we will use 0, 1, 2, 3. If in 2 consecutive cycle, if we would have used the same weights, then the weight read would have been lesser. Remember, our P, in our P structure we just had one buffer for the weight. So, if we are changing the weights every cycle, that means we have to read the weight from the memory. We cannot store in that buffer, right. So, that is why the number of weight read is also E multiplied by R, number of input read is also E multiplied by R, because at every cycle we are actually changing the input. Interestingly, number of output read is 0, because we can store that output, like the partial output, in that one single buffer of the P, so that we do not need to read from the output buffer, output activation buffer, right. So, as long as we do not need to read from the output activation buffer, we do not need to do a output read. That is why the output read value is 0. But output write has to be E, because once one particular output is computed, that has to be written in the output activation buffer. So, since we have total E number of output, the total number of output write will be E. Okay. Now, let us see how can we make one architecture or one hardware which is specific to output stationary data flow. So, remember, the basic building block of the hardware is the P, right. Now, let us say we have these P, P0, P1, P2, P3, P4, etc., right. Now, from the in the output stationary data flow, our target will be from each of the P we will get one specific output, right. So, to get that we need to broadcast the weights to all the P's, so that each one has W0, W1, W2, W3 whenever they need it. So, remember, to get each of the pixel in the output or each of the output in the convolutional layer or in the convolutional operation, we need all the weights, right. So, that is why weights needs to be broadcasted to all the P's, right. Now, according to the sliding window of inputs, we need to distribute the required inputs to all the P's. So, for an example, P0 will get I0, I1, I2, I3, I4, or sorry, I0, I1, I2, I3. P1 will get the next sliding window I1, I2, I3, I4, and so on and so forth. Now, all the P's, now as soon as all the P's got the weights as well as the input activation, we can perform parallel computation to generate the outputs. So, once all the P's get all the weights as well as all the activations, each of the P can do a parallel computation to generate the output 0, output 1, and so on and so forth. So, overall in output stationary data flow, we have to get all the we have to compute all the partial sums for a particular output, as long as the whole computation of the output is not over, right. And if we want to make one architecture corresponding to this output stationary data flow, then we can have multiple P's, and we have to arrange the data flow and arrange the architecture in such a way that each of the P will give us one particular point or one particular output. So, that is the output stationary data flow for us. So, that is all for this particular lecture. In the next lecture, we will see other data flow as well as the comparison between different data flow. Thank you very much. See you next time.